Okay, is this on? Yeah, okay. Cool, hi everyone. So there's a lot to unpack in the title of this paper, but the central thing is the central word there, collaborative. So programming is collaborative. You always start with an obvious statement in a talk like this, right? I mean, you know, we use a lot of different tools to collaborate with one another on software. Perhaps central to that are version control systems. I'm going to use Git in our examples. There are many others, Darks and others that are very interesting. And then there's kind of these social coding platforms like GitHub and GitLab that are built on top of that. Some of you might also use collaborative editors, so think like Google Docs but for code. So there's like Visual Studio Code Live Share and other tools like that. So I'm going to mostly focus on the version control in terms of terminology and examples, but for the purposes of kind of this talk, a collaborative editor like this is just a really fast, kind of fine-grained version control system. Right? You're propagating the changes continuously rather than in batches of commits. So we're at POPL, so why is this a programming languages problem? Well, central to these tools like Git is a programming language. You've probably seen the patch language, the Unix patch language. Fun fact, who knows who invented the patch language? Nobody? Larry Wall, yeah, of Perl fame, the second most popular programming language. So the patch language is a very simple language. It's kind of like a little imperative language on how to edit a file to change it into another file, right? So it is a programming language, but of course you could be forgiven for not knowing the inventor because we don't generally write programs in this language ourselves, right? Patches are synthesized, if you will, from the file system state, from two different versions of a file. So you use diff, which is a program that generates patches from two different states. And then, so the kind of central way in which we collaborate with one another is by sharing patches with one another through version control systems like Git. So let me just set up a really simple example to set up some of the problems with these current systems. So let's say you have this like 2-line file, and Alice and Bob are both editing this file separately. So Alice renames this function f to append, and Bob adds an argument and does something with that argument. And so you can see what the generated patches would look like there. And then let's say Bob shares his patch with Alice. Well, then you need a merging algorithm, right? You have to do a merge. And so the merging algorithm that's typically used is what's called a 3-way merge algorithm, where you actually take all 3 of these things, the base branch and the 2 patches, and you try to merge them together. So what's going to happen when we merge this? So the answer is a merge conflict. And this seems like just part of the water in our programming ecosystem that these kinds of things are going to happen here. So in particular, that line that starts with a def was modified by both Alice and Bob, and so there's a conflict there. But because it's a 3-way merge, the base branch and Alice's branch don't diverge on that return line, and so Bob's change is not conflicted there on the last line. Now, I would say that this is already a problem because of a sort of a granularity issue, right? These patch languages operate at the level of lines. Kind of morally, right, the change that Alice made to rename this function is independent of the change that Bob made to add an argument. So it would be nice if this wasn't a conflict, but it is a conflict. But let me give you a kind of more pernicious example that could actually cause real problems that you might not immediately detect. So let's say it's the same setup. Alice and Bob are both making the same edits to this function, but also they both have different views on where in the code base that these functions should go. So they both relocate these files to different locations. I'll call them new location 1 and new location 2. So from the perspective of patch synthesis, what happens here is, well, it looks like a deletion of the original function and an insertion of the new version of the function in both of those locations. So given these 2 patches, what happens when we do our 3-way merge? It works and the code is duplicated. There's no merge conflict, despite the fact that we had the same edits as before and one more conflicting decision was made about where the code should go. So why is that? Well, the version control system didn't see the actual edits. The programmer's actual edits were lost, and so you have to use heuristics. These patch synthesis systems like diff, as wonderful as they are, right? They are heuristic systems that have to infer what must have happened in the editors that you were using from changes to the file system state. And code relocation, especially when that's like independently, but also especially when that's combined with edits to the code, it's just impossible to tell whether that that function f and that function append were from the same place because they have changed so much, right? And these systems often have like heuristics. If it's changed a certain percentage, it's treated as a relocation. It's like very brittle and messy. So this is, I would say, fundamentally problematic. So what is the solution? Well, what we can do is we can just eliminate pat synthesis entirely. So I'm going to talk about version control without diff. How do we do that? Well, we just saw a great talk about structure editing, right? So what if we could actually record the edits that the programmers performed, including the code relocations, and then share those patches that were derived directly from our actions rather than inferred heuristically from file system changes? So we're going to do this in the setting of structure editing. I think actually there's parts of this talk that could go into plain text editing as well. But to also solve that granularity problem that I talked about earlier, structure editing is a really nice platform and also work that my group does. So we already saw a talk about structure editing, but just briefly, what is a structure editor? It's an editor that at its heart has another programming language, which is actually kind of going to align with this patch language idea, this edit action language. This is a language that directly transforms program structures. You can think of these as syntax trees with holes, or in synthesis, it's called a program sketch. So there are lots of interesting examples of structure editors in use today. In my freshman class that I'm teaching this semester, I did a show of hands to see how many people learned programming with Scratch, and it was like half the class. So lots of people are learning how to code in Scratch and Snap and other tools like this, these block editors. We just saw Pantograph, really cool structure editor that has some interesting type directed features. There was a mention of Hazel, which is the tool that we are building, the structure editor that we're building in my group. This talk isn't specifically about Hazel. The ideas apply generally, so I'm not going to give you a Hazel demo or anything, but ask me for a demo. I think if you're the kind of person that sort of like looked at structure editors in the 80s and 90s and decided they're not usable, I think we have arrived at a new point in that design space. So I'm happy to give you a demo and convince you that actually they are usable now. And Tyler is the system that we are developing to generate structure editors from grammars for JavaScript and other languages. So expect to use a structure editor in the next decade, I would say. There's lots of other cool examples. JetBrains has MPS. There's Lambda. There's lots of others out there. So if you allow yourself to use a structure editor, then you can derive patches directly from structure edits. Oh, sorry, that's a video. So what about merging? Okay, so that's really like we can share the edits, but how do we merge edits together? So the usual approach in both kind of version control systems and kind of real-time collaborative editors is to define an operational transform. So the three-way merge algorithm, this is kind of underappreciated, is an operational transform. The idea is for every pair of actions that might be kind of sequenced in a change, you have to define a transformation of the second action to make sure that the order doesn't matter anymore. So you could do things like shift the indices of like line numbers and column numbers and things in the second one so that they're shifted by the appropriate number of insertions that happened in the first one. So this is fine, and there's lots of interesting work on operational transforms for various kinds of data structures, but it's very involved, it's very specific to the action language of each editor, and it's very brittle. Every time you make a change, you have to like prove all the properties about the convergence. So I'm gonna do something, so I already said I'm going to get rid of diff. I'm also going to get rid of merge. Instead, what I'm going to do is I'm going to define an action language where there is no need for a operational transform because all of the actions commute without transformation. You just literally share your edits with one another and play them in any order, and you converge on the same state. Okay, so that seems interesting. So the underlying ideas have been explored in the systems community, the distributed systems community, under the rubric of CRDTs or CmRDTs. This stands for commutative replicated data type. So the idea of a data structure where all operations commute is very old. The systems community kind of discovered that this is really useful for distributed systems in the 2011 or so. So classic examples are one-phase sets. So a set where you can only insert naturally commutes. You can only do insertions, and order doesn't matter. There's two-phase sets where you can also do deletion of things, but deletion is permanent. So there's this idea of a tombstone where something is permanently killed off once it's deleted from the set. So that also is commutative. So there's lots of other examples. So we're going to define a CmRDT. Okay. So if our editor state were a CmRDT, like I said, merging would reduce to applying remote actions directly without transformation. But this is easier said than done. Like typical structure editing actions don't commute by default, right? We had a paper at POPL 2017 on a structure editor calculus. By no means do those edits commute. So how do we make them commute? Well, what we've done in this paper is we've defined Grove, or the Grove patch language, which is what you can think of as sort of an intermediate representation in IR that structure editor action languages can translate down to. And it's a very simple language that provides this commutativity property. And I'll detail it in a few slides. But I just want to note there has been some prior work on tree CmRDTs. But there's a couple of things specific in the coding space that we want to make sure we support that prior work hasn't supported. So one is that sometimes you get commutativity by resolving conflicts kind of arbitrarily and consistently. That's not what we want to do. We want to explicitly represent conflicts so that the humans involved can mediate conflict resolution. And then a lot of these systems don't have support for relocation, which we think is really central to actually represent that explicitly rather than just insertion and deletion. So the Grove patch language resolves these issues. And kind of the key insight is that although we are working with trees, syntax trees, we have to kind of project this into a larger space of label-directed multigraphs. So we're developing a CmRDT for label-directed multigraphs. But then we'll get back to a collection of trees, which we'll call Grove, that contain explicitly represented conflicts in addition to wholes. And these things have to be linked with one another. So it's a collection of trees for a reason that I'll show you in a bit. OK, so let's do some examples here. OK, so actually, this would be a lot easier if I could point on my screen. No, not like that. Sorry. OK, I'll have to look this way. OK, so like I said, the central idea is to represent our program state. I'm just going to use simple expression language with just arithmetic for our examples here, but this generalizes. So we represent our state as a graph. We have a special root node. That's the dot there. So each node has a kind of a constructor for that AST node. And then we have unique IDs on all the nodes as well. So that's unique ID 0, 2, and 4 there. And then you have edges between them, and the edges are labeled by a position. So the root node has one position, root. The times node has a left position and a right position. In this case, there is an X on the left, so that's labeled with L. And the edges also have unique IDs. And then there's no right node here. And so when you decompose this graph into a tree, you leave a hole in that position. So there's no edges there. OK, so that's kind of our starting state. Simple edits kind of behave as you would expect. If I want to fill that hole Y, that hole with Y, I create a new edge and a new vertex. Technically, what happens is when you create an edge, it mentions a vertex, and that vertex becomes created when it's mentioned by an edge for the first time. So it's really edge insertion and deletion is the core of this Grove patch language. So we've created our Y. Deletion is also edge deletion. Notice that the node, the vertex X, is not deleted. It's just the edge that's deleted. And this is really critical to the whole thing, is edges are the thing that are being edited. Vertices, when they come to life, they live forever. OK, so one way to think about it in terms of CmRDTs is that vertices are one-phase sets and edges are two-phase sets, because edge OK, so some kind of user-facing edit actions correspond to a sequence of multiple kind of patch actions. So if you want to wrap the times node from the last state here with a plus node, that amounts to temporarily disconnecting the times node, creating the plus node, and then reconnecting the times node. That would be kind of atomic from the perspective of a user, but in the patch language, that's multiple steps. And then code relocation is also just sort of edge deletion and insertion at the new location. So nothing actually gets, no vertices that get deleted. It's just that the previous location of the times on the left here gets relocated by deleting the left edge and replacing it with a right edge from that parent or from whatever the new parent is. OK? So that's just kind of the single user perspective. Now let's talk about collaborative structure editing in Grove. So the diagram that we're going to use here, so this kind of a legend for what you'll see in the following slides is Alice's edits are in red, Bob's edits are in green, you'll kind of see them. And then the squiggly blue line is the convergent state that arises when they share their edits with one another. Okay? So at the bottom there, you see the key theorem, which is this commutativity theorem that says, for all graphs G and G prime and all graph patch commands pi1 and pi2, a graph patch command is literally just add or delete and then an edge ID, or an edge. If you do this kind of editing transition in one order, it's the same as doing it in the other order. So a very simple commutativity theorem. Okay? So let's do a couple more examples. So in this example, we start from the previous state, and what Alice does is she fills the hole in the multiplication with u here. Bob does something independent of Alice, but in the same expressions, or sort of on the same line, renames y to v. Those edits get shared in terms of the edge insertions and deletions, and they kind of don't interfere with one another. There's no conflicts, and so everything merges cleanly, and they go on with their day. So that solves this granularity problem. This is just a single expression, but it doesn't matter. There's no notion of a line in this system at all. Another example, Alice renames U to W. Bob relocates the parent of that node that was renamed to another place. This was the problem that we saw earlier where you would get that silent duplication. You don't get that here. The edit kind of moves with Bob's move because of the way the edges are set up. The edges are just changing the parent location, but everything downstream of that edge kind of gets moved along with it, and so everything commutes cleanly, and there's no conflict to resolve there. So now let's talk about conflicts. So conflicts are kind of inherent, right? You can't actually get rid of conflicts, but you minimize them and represent them explicitly. So here's a simple example. If Alice fills this hole here with x, and Bob fills it with y, well, there's no kind of obvious resolution to that, so you kind of punt it back to the two of them to resolve by representing it as a conflict, which is written like this. And in the graph, this is a multigraph, so you can actually have multiple edges labeled R coming out of plus, and that's fine. And it's just when we decompose this graph back to the term, it turns into a conflict because there's two things in this right position of the parent. Okay. Now you can also have relocation conflicts. This was what we talked about earlier. If Alice and Bob both decide to move the same thing to different locations. What's that? Okay. Okay, so similar idea. You kind of represent the conflict explicitly in the term because this is a node that has two incoming edges, which is not typically what you want in a syntax tree. So there's other things like this. Unicyclic relocations can happen if you do the right combination of moves, so we have a representation for that. Ultimately, what you get is a decomposition from graphs to groves, which is this idea of turning the graph into a collection of terms. I had suppressed all the unique IDs in the terms, but they're all kind of fundamentally there. And then we can decompose that set of terms into kind of like a classification, which we call a partition grove, of like whether they have one parent, multiple parents, deleted, etc. So we have a little UI for exploring the calculus called the Grove Workbench that you can play with and instantiate with your own syntax tree representations. And then the kind of one last thing in the paper is so far we've just been talking at the syntactic level, but we also have a bidirectional type error localization system for groves based on our paper from last year. So I won't talk too much about that, but it's in the paper. Basically, we instantiate the system with a lambda calculus. We figure out all the ways it can go wrong, including merge conflicts of these various sorts. And then we assign a type system and a type inference system for that generates constraints between the conflicting things so that you can kind of like reason about programs with conflicts. So in the paper, full formalism, everything's mechanized in Agda. There's more details on the implementation there. I thought this was a nice quote. I'll just read the first bit of it. So this was from the developer of Darks in a paper called Theory of Patches. The fact that commutation can fail in Darks makes a huge difference in the whole patch formalism. It may be possible to create a formalism in which commutation always succeeds, ... This might require something like an anti-file, which would annihilate with the file when the file finally gets created. So that was like kind of the right track, this idea of a permanent deletion, but it wasn't the vertices that are permanently deleted. It's really, to solve this problem, you need to think about it in terms of edges being permanently deleted. So I'll just conclude with kind of the big vision that this project is a part of. So a quote from an interview by Alan Kay. Someone asked him about Wikipedia, and he said, it's a tremendous collaboration, but go to the article on Logo. Can you write and execute Logo programs there? No. So what if we had programs the size of Wikipedia being collaboratively edited live, type checked live? What if GitHub were truly a live commons instead of just a collection of siloed repositories? So this is exciting to you. Hopefully you can see how that connects to this paper. And there's a vision paper on some of these ideas from last year's POPL workshop at hazel.org. Happy to talk more about any of this. Thanks.
We have time for one quick question.
This is great. I take back what I said about I've been working with Hazel the last, you've been talking about. It's pretty awesome, although I got it to hang several times when I did non-structured
production grade yet.
But it's super. This is so cool. What if I want to do this for TypeScript? Like different languages. I mean, what do you need in terms of the language and the type system? Also the keywords to make this whole work.
Yeah, so I mentioned this Tyler system that another student in my group is working on, David Moon. So there you can kind of input the TypeScript grammar and get an editor like the Hazel editor. Hopefully a future project will be combining this paper and that paper, so you'll get a collaborative structure editor for free from the grammar. And then the type system, I think that's last year's paper, ... We could talk offline about it, yeah.
Thanks.
Thank you.